This is Professor Behrang, and the topic of today's lecture is ideal gas law. This is the second lecture of fluid mechanics. So let's get right into it. If you have watched the first lecture of fluid mechanics, we went through a bunch of definitions, and one of them was state and state postulate. When I talked about state postulate, I said that if you know two independent intensive properties of a substance, the state is determined. By that I mean, if you give me, for example, pressure and temperature of air, I should be able to give you its viscosity, its Cp, its internal energy, enthalpy, entropy, other properties, and that's state postulate. And we also talked about the fact that the equations that kind of relate the state, the properties to each other are called equations of state. So ideal gas law is the simplest form of an equation of state, basically. Equations of state, if you end up going to grad school, are way more complicated. But ideal gas law is the simplest form of an equation of state. First, we start with this. What's an ideal gas? An ideal gas, basically, it's a gas that follows the ideal gas law, mathematically. That's probably the most accurate definition of an ideal gas we can give you. But there is actually a physical meaning to it, and then this lecture is about how to use the equation. You can look at thermodynamics books and things like that and figure out what the physical meaning is. Okay, so let's get right into it. What's an ideal gas law, and how do we use it? And that's it. So ideal gas law is, think of a container. Let's say we have a container like this. This is our container. And let's say, for the sake of this example, we have air in it. Air follows the ideal gas law. A lot of gases actually follow the ideal gas law. Gases that have small density and when the temperature is so high and pressure is low and eventually the density is small, gases act like an ideal gas. But when we talk about air, the pressure is not that small. It's 1 atmosphere, and the temperature is not that high. It's probably 20-25 degrees Celsius, and it is still acting like an ideal gas. So air, nitrogen, helium, argon, a lot of gases, in fact, act like an ideal gas. They follow the ideal gas law. I recommend that you look at thermodynamics books, and then there are some charts that basically they help you understand more the physical meaning of the ideal gas law. As I said, this lecture is about how to use it. So imagine we have a container and we have air in it, and the temperature of air is given, okay, after it reaches equilibrium in this tank, and it's a closed system, right? And then and the pressure is also given. Okay. What is ideal gas? Ideal gas is basically this: P times the volume of this tank equals N, number of moles of air here in this tank, times something called the universal R sub U, and T. The first thing that I need to point out when it comes to ideal gas is, first of all, these equations that we deal with, you have to, you can use English units for this one too, but it's kind of tricky. But in SI units, you have to use basic SI units for this case to work. By that I mean this needs to be pascals. This needs to be meters cubed. This is Kelvin. Basic SI units for temperature is Kelvin, not Celsius. Celsius is an SI unit, but it's not the basic SI unit, right? Okay. And what you have here is the number of moles. So let's say we're dealing with air, number of moles. How do we find number of moles? Number of moles, in fact, can be calculated using this equation. The whole mass of whatever we have in this tank over the molar mass of air. Molar mass, what's the unit of mass? The unit of mass is kilograms in basic science. What's the unit of molar mass? Is kilogram per mole. That's what it is. As a result, when you actually, try to find the unit for the universal R, and then we're going to get to that to tell you what that is, becomes the unit for universal R is joules per mole Kelvin, like this. The universal R has a certain value, and this value is correct for any ideal gas. Any ideal gas has the exact same number that I'm going to write for you. The value is 8.314 joules per mole Kelvin. That's the unit for the universal R. Okay, good. Now, there is one more thing that I need to mention. In ideal gas law, you can never use gauge pressure. So when we talk about pressure, which is this term here, right, you have to use absolute pressure here. You do not use gauge pressure. If gauge pressure is somehow given, you have to find the absolute pressure of the pressure would be the pressure in the tank in this case, and then put it in ideal gas law, right? And you have to use absolute temperature, which is Kelvin. Do not use Celsius. If you have Celsius, you got to convert it to Kelvin and then use it. You never, ever use gauge pressure in ideal gas law. Always the absolute pressure. That's very important. Now I want to show you another form of ideal gas, which is more actually popular when we use it in thermodynamics and, heat transfer and fluid mechanics. The other version is kind of like this. Okay, so we said P times the volume equals N universal R T. And universal R is 8.314, sure, and joules per mole Kelvin. Now, I can rewrite the value of N, the number of moles, this way. I can write it this way. I can say PV equals the mass of air in the tank in this case, over the molar mass times the universal R times T. And then I can rewrite it as P times V equals M times universal R over M times T, something like this. Now, I can go ahead and call this guy, this value that I have here, this guy, just R. I can just call it R, which is the universal R over the value of the molar mass. Every gas has its own molar mass. Let's give you an example. For example, when we talk about air is about, let's say, 80% nitrogen and about 20% oxygen, right? That's our air. As a result, then I can calculate the molar mass for air as about 80% of nitrogen. One nitrogen atom is 14 grams, and then two of them would be about 28 grams, right? 28 grams plus about 20% of oxygen. One oxygen is 16. O2 is 32 grams times 32 grams. Then I get something around 29. It would be like 28.8, something like that, but about 29 grams, something like this. That would be the molar mass for air. But I can also rewrite this as 0.029 kilograms in basic SI units. Now, if I want to calculate the value of R, not the universal R, I know what it is, 8.314. If I want to calculate the value of R for just air, the specific R for air, then I can do that. R for air in this case would be 8.314 joules per mole Kelvin divided by 0.029 kilograms, which gives you a value very close to 287. The unit for this one, however, that would be kilogram per mole, by the way, the unit for molar mass, would be joules kilogram Kelvin, because the mole part gets cancelled. This is R for air. I always recommend this to my students that memorize R for air, memorize it. Because, yeah, you don't need to memorize R for every gas that you deal with. But for air, because we deal with that a lot in a lot of problems, go ahead and memorize it. It's a good investment. 287, that's the R for air, right? So now now I can rewrite the ideal gas law like this. I can say P times V equals M R for times T. Now this R is specific. This R is not a constant number for every gas. Yes, it is constant for air, but once you switch from air to nitrogen, then it's a different value of R, as opposed to the universal R, which was supposed to be the same for all of them. Now, but we got the mole out of the way, basically. Now we're dealing with just mass of air in a tank, which is probably better. So this is one version of it. There's another version of it that actually is more like an equation of state. This is an equation of state anyways, but I can get density out of it because we talked about equations of state. Equation of state, when you give it two intensive independent properties, you can get other intensive properties out of it. I can get one more intensive property out of this, and that's density. Let's get it. I can rewrite this whole thing as P equals M over the volume times R times T. And then, of course, M over V, what is it? That's density. Now I can rewrite this as P equals density RT, like this. That's the pressure, and that's density. So, okay, let's take a look at the units one more time. This unit has to be Pascal. This unit is kilograms meters cubed. This unit is joules, kilogram, Kelvin, and this guy is Kelvin. And you never use gauge pressure in ideal gas law. How many times did I say that? Be careful about it. That's how we use ideal gas law. Okay, so there's another version of R that when you look at thermodynamics books, sometimes you get the value of R, which is supposed to be joules per kilogram Kelvin. Sometimes you get to read it in terms of kilojoules per kilogram Kelvin. In that case, R of air is usually written as 0.287 kilojoules. This way. Kilojoules kilogram Kelvin. That's not a problem, but you got to be careful. If you're using kilojoules per kilogram Kelvin for R, then you have to use kilopascals on the other side of the equation. If you don't want to get confused, go back to basic SI as always, and the equation works all the time. But I write it one more time. So if you want to use the other version of ideal gas law, which is still the same version, equals MRT. If somehow you decide to go with kPa for the pressure, volume stays meters cubed still. This is still kilogram. This becomes kilojoules per kilogram Kelvin, and this still stays Kelvin, right? So everything stays the same. Okay, now our goal here is to use that in an equation to learn how to use it. And that's what we're going to do in the next example. And I forgot to tell you at the very beginning of the video, always take a piece of paper and a pen and start taking notes for my videos. The act of writing basically gets it in your nervous system and you learn. So before we talk about the example, if you're getting some value out of this video, make sure you subscribe to this channel. Also send this content to a future engineer or somebody who you think might benefit from this content, because by word of mouth, basically you can help me grow this channel. So let's take a look at a problem. This is a problem, so I appreciate it if you just pause the video and read this problem, and then get a piece of paper, everything, and your calculator, and we can solve this problem together. Okay, so I hope you read it. What do we got here? We have air pressurized in a tank. The pressure is 140 psi absolute. Notice that it says PSI absolute, PSI A. So that's good. It's not a gauge pressure, so I don't need to worry about it. That is gauge pressure, because if it is a gauge pressure, I need to know the ambient pressure so I can calculate the actual absolute pressure and put it in the ideal gas law. Then there is another problem here. This one is given in gallons. Okay, I got to convert it to meters cubed. I got to convert this guy to Pascal too. So this needs to be converted to pascals. This one needs to be converted to meters cubed. Make sure. And this guy in 45 Celsius needs to be converted to Kelvin. I need to do this first before I can use the ideal gas law. What's the goal? The goal is the mass. We need to find the mass of air in the tank. Okay. This is something that I always recommend to my students. Before you actually put in the numbers, try to solve the problem parametrically with just the equation to see if you have enough equations to solve the problem. This problem can be easily solved using ideal gas law. Let's just write it. What am I looking for? M. Which version of ideal gas law has M in it? PV equals mRT. I can rewrite it in terms of P equals rho RT, but it doesn't ask for density. It is asking for the mass. So the other version that has mass in it would be a better deal for me. So I'm going to go with that. So this would be the equation that that will help me out. PV equals mRT. It is air. So I told you that to memorize, airs R, and then airs R has to be 287 joules per kilogram Kelvin. Okay, got it. Now, how do I find mass? Looks like in order to find mass, I gotta just play with that equation, and M becomes basically P times V over R times T. The only problem is I need to convert pressure from PSI absolute to pascals, V from gallons to meters cubed, and T from Celsius to Kelvin. And that's what I'm going to do. So the equation, pressure is 140. 1 PSI is about 6.895 kPa, and 1 kPa is 1,000 pascals. Okay, so I got the pressure. Then what else do I need? Well, I need the volume. Volume, 1 gallon is about 3.78-ish liters, and 1 liter is 10 to the negative third meters cubed. So that would be 120 times 3.78 times 10 to the negative third meters cubed, like this. And finally, temperature, I have 45 degrees Celsius plus 273.15 if you want to be like exact, but that's fine. Kelvin, that would be, now everything is good to go. Now your final job is basically just put the whole thing together. Mass becomes just 140 6,895 times 10 to the third, this is pascals, times 120 times 3.78 times 10 to the negative third, this is meters cubed, over 287 joules per kilogram Kelvin times 45 plus 273 Kelvin. Go ahead, use your calculators and basically do it and see which of these answers you will get. You can pause the video, do the calculation, and then look at the answer. Okay, let's say you pause the video and you did the calculation, and the answer that you will get will be this number. Seems like this one is the answer. So, but when you look at this whole thing, there is a couple of other numbers. There's 48 kilograms, which is incorrect. There is also this guy, B, and there is A. One of these answers, and I think it's A, if instead of, this is wrong, right? Instead of Kelvin, if you use Celsius and you forget to convert Celsius to Kelvin and you use it in ideal gas law, you're going to end up with A. So Try that at home, see if you get that number. The correct answer is C, 4.8 kilograms. Okay, I hope you got something out of this video. See you in the next video. Again, write down in the comments what else do you want to know about fluid mechanics. See you in lecture 3, and make sure you subscribe and send it to somebody who is doing also engineering and mechanical engineering. Thank you.